Yep. Okay. Hello, guys. Welcome to the class. My name is Saravanan. I'm with Trescore Networks. Unfortunately, Dauda couldn't join today. So today's topic, we're going to cover the wireless and the networking concepts, primarily the networking concepts, but we'll also touch upon some wireless radio concepts. So if I want to see, so one of the things that we want to do today is just to understand what is actually inside a wireless router. Okay, so what are all the pieces that are running inside that box to make things work for you? Okay, um, like for example, has a DNS con.
Sarvan, can you speak loud? Not able
Okay,
to hear. Okay, good. Thank you.
okay, yeah. So today we'll just look inside what's inside this wireless router that you have at your home. And what function it does to allow your devices to browse internet or print, or your IoT devices to monitor, function, log, whatever it does. Uh, Basically, these wireless routers are like a mini or micro, but a basic version of an enterprise networking and security infrastructure that is packed into this tiny little device. Okay. Um, so before we dive into the details uh, of all these concepts, let's briefly go over the wireless communication and concepts. Okay, basics, just the basics. Um, so let's just start by looking at the electromagnetic spectrum. I mean, this is not going to be like a physics class, but just some basics. Okay. Um, as you all might already know, the electromagnetic spectrum is classified by uh, wavelength into radio, wave, microwave, infrared, ultraviolet, X-ray rays, and gamma rays. Okay, and in the middle is there is a visible spectrum. That's the things that we can see. I mean, we don't have to go deep into all these. Um, so the radio frequency portion within this electromagnetic spectrum is the one that we are going to concentrate on. So this spectrum is actually regulated by almost all the countries over their airspace. The usage is actually regulated. You can't just randomly transmit um, data um, or any form of communication over those frequencies. But within that range, there are some specific ranges that are allocated for um, as a free spectrum, they call it, or sometimes they call it as a garbage band because it can be used by multiple devices. You don't have to actually get a license for it. Okay, so before we go there, we can just say who actually maintains these things. The in in the US, the FCC administers the spectrum, and mostly for non-federal use. And there's another organization, NTIA, is the one that's administers spectrum for like federal use, like for example, Army, um, FAA, Federal Aviation Authority, and the FBI, those kind of organizations, NTIA regulates. And so within that range comes these ISM bands, or they call it um, industrial, scientific, and medical bands. Okay, so those the name basically was derived by because originally these bands were used for like microwaves, cordless phones, um, RF weldings, multiple other things like medical and scientific equipments. So that's why that name was derived. And it was a free unlicensed spectrum. And within that spectrum, the ranges that was mentioned in the previous slide is the one that was allocated uh, uh, for those ISM bands. Two of them in particular was adopted by the Wi-Fi Alliance, or when the IEEE 802.11 was formed, or they derived, or they actually researched and did the development work. They chose two of those bands, um, the 2.4 gigahertz band and the 5 gigahertz band. So this is what you'd mostly see in most of your Wi-Fi setup these days. So initially, when they started out with um, 2.4 gigahertz. It's all happened in 1999, and then they also introduced the same year 5 gigahertz range also. Uh, the the one thing that you need to note about 2.4 gigahertz is if you happen to have like a old microwave oven or cordless phones, you'd see actually more interference with this um, 2.4 gigahertz band. Okay, um, so let's see. Let's see how they developed from 802.11. That's how they started out. Initially, they didn't assign these. The Wi-Fi Alliance didn't assign these numbers and names. They were actually referring them as 802.11 BA, like this. Then they adopted this naming standard. So right now, if you look at all the latest Wi-Fi, if you look at your Wi-Fi router, if you buy a new box of Wi-Fi router, you would see some symbols that denote what type of Wi-Fi device it is. Okay. Um, so let's see what 802.11 actually, what is IEEE. I'm sure a lot of people here already may know. It's an alliance that was it was like a group of people, big group of engineers, electrical and electronics engineers, who contribute to research and development, and also they set standards and protocols to create like a framework for people to follow, and also the industry to adopt. That way, there is no contention, right? So they basically, it's like a set of standards and protocols. And so after 802.11, Wi-Fi was basically demonstrated or developed. The Wi-Fi Alliance was formed. It was actually established by a
Saravanan,
yeah.
they are asking you to present the slide so that it will become much more bigger.
Oh, okay. Is that better?
Yeah.
Okay. So then the Wi-Fi Alliance was established. It was actually established by a group of leading wireless technology companies. I mean, at that point of time, um, just to promote the wireless as a means of communication, right? And also set some standards and interoperability, basically standards. Okay. They also handle the testing of the Wi-Fi products. For example, if some company wants to develop a product, Wi-Fi product, they do testing for compliance, and also they basically provide them a seal. So basically, when you see a Wi-Fi logo on a vendor's or a company's Wi-Fi router when they're selling, that means it's actually it's been tested and it's compliant with the IEEE standard. Okay, and that logo is actually a trademark for those Wi-Fi Alliance. I mean, it's trademarked by the Wi-Fi Alliance. But just to know that all these companies needs to go through a standards and compliance protocol before they can sell any of these devices. Okay. So it evolved basically as a device that started using 2.4 gigahertz, and then they developed 802.11a. The reason that B is given in the thing is because they started using an alphabet order, and actually A and B came out the same year, but because they adopted this first, it was 2.4 gigahertz. And then they developed 5 gigahertz. 5 gigahertz is slightly better in performance when it compares to 2.4 gigahertz, but it also has its own limitations. It cannot travel longer. It actually interacts more with the surroundings than 2.4 gigahertz. Like for example, if you see the spectrum, anything that has lower frequency, right, or higher wavelength, you will always have better performance with respect to how far it can reach. You can also think of like why would they choose a red color for a traffic light instead of choosing some other color. The reason is red actually travels much farther than the other colors. That's why from the visible spectrum, when they did the traffic lights, I don't know when in the past, they chose red as one of the colors to alert people that they have to stop. Okay. The basic reason is actually when the frequency is low, it has less time or less interaction with the atmosphere, basically, right? If you have a high frequency, it interacts more with the atmosphere and the medium that it goes through. So similar concept, anything that's lower in the frequency, like 2.4 gigahertz, radio can actually travel farther than the 5 gigahertz band. Okay. Similarly, for example, radio waves, maybe like of few hertz, they can travel like thousands of kilometers or miles. So same concept. Just remember that 2.4, even though it's in the garbage band with microwaves and cordless phones and multiple other Bluetooth and multiple other devices in that range, it's still the band that can actually travel further than the 5 gigahertz range. Okay. So after 802.11a, they did 11g with .11g. They actually improved the performance, the data rate that you can achieve to 54 megabits per second, and but it was still 2.4 gigahertz. So this is when the actual change happened. It actually made a dramatic difference when they introduced 802.11n, when they actually supported both 2.4 gigahertz and 5 gigahertz radios in the same box. Okay, so if there are any devices that are old, and basically any device that has wireless network adapter in it, in the olden days, basically every electronic chip or electronic device was expensive compared to these days, right? So it was premium to have devices with 5 gigahertz during those days. So any of these small old laptops and all those, they had only 2.4 gigahertz. So if you have a mix of 2.4 gigahertz and 5 gigahertz devices, you can actually support both of them. You can have two separate bands, like one of the bands, 2.4 gigahertz band can support all those old devices, and all the newer devices can actually use the 5 gigahertz band. Okay. So before we go on to the AC and the AX, there's one more AXE that is coming up. Let's just look what are the pain points that actually made them to look much further than 802.11n. So I just covered these. So generally, when you look at the Wi-Fi, it's not like a wired communication, right? If you're a wired communication, you'll have a transmit. If you look at, like, for example, an Ethernet cable, the one that you use in, I don't know, most of the homes don't even have Ethernet these days. There will be a transmit line, there will be a receive line, right? So that you can send and receive. Whereas in wireless, it's a single medium. It's not like a directly connected end to end. So it's a problem. So in Wi-Fi media access control, or in this medium access control, the medium is the air or the space in between the wireless access point and the clients, right? So what they did was to make sure that the radios in the past, to avoid collisions, the antennas or the radios that wireless router or the client use, they are supposed to talk one at a time. Okay, and the if you don't have a wireless router, if you have some other technology that everybody is talking at the same time, it won't, because there will be interference, because everybody's on the same channel and everybody's talking at the same time. It will be almost like a classroom setup where a teacher is asking a question and nobody's following any, I mean, they're not raising their hand or getting a nod from the teacher to talk. So radio is similar, right? If everybody's talking, everybody can hear. And that is a perfect example of interference, similar to the way the wireless works. In wired, basically, you can connect all these individual people into a switch, network switch, and then you can control how people talk and how we can avoid those interference. But in wireless, the radio, the frequency, if everybody talks, there is an interference. So at the end of the day, you would not get the data transferred. So they introduced a concept. Basically, it's a carrier sense multiple access. It's collision avoidance. That's what it says, right? What they do is the Wi-Fi device is the one that, or the access point. You can even call it access point. It creates basically, if a laptop wants to send, it sends a request to transmit, and the Wi-Fi or the access point sends a clear to send, request to send, clear to send, and that clear to send is received by everybody else because it's open air. Everybody can listen what is being put on the air, right? And they know that, okay, I think somebody else is talking, so I should not be talking. But in the meantime, they constantly check by sending their own RTS, request to send. But the Wi-Fi, until it tells, okay, now you are clear to send, that device just keeps quiet and then keeps retrying. Okay, so just imagine like a school classroom setup, if you want to understand, as an analogy for media access control. Okay. The other concept that you would want to understand is, nowadays the routers come with multiple bands. Like when you're buying a router, you'd see it's a single band router, dual band router, tri-band router. All those have popped on these days, right? single band routers, they broadcast only one band. Like for example, if you have a device, if you have a 2.4 gigahertz router, that's only say 802.11 B, and 802.11a will be only 5 gigahertz, right? But if you're assuming you have a 802.11, you have an option to have multiple bands. You can have 2.4 gigahertz radio and also 5 gigahertz, both of them in the same box, right? So they came up with the idea of having multiple bands so that devices that are slow or the older devices that work only on 2.4 gigahertz, they actually can use the 2.4 gigahertz, like in this analogy, for example, trucks, assuming trucks which move slower than the cars take their own lane in a highway. And also the newer routers have tri-band, which basically has three bands, tri-bands. They have two channels or two bands dedicated for 5 gigahertz bands. Basically, the crowding is avoided. For example, in the olden days, I think normally homes have had like maybe 4 or 5 devices. Nowadays, there are like 20, 30 devices in every home. So even if you had two bands, this 5 gigahertz is the one that most of the devices are using. This band will be crowded also. So now they have the third band, tri-band radios, tri-band routers are also being sold these days. Okay. Yeah, just look at remember the analogy of the highway with the trucks and cars when you're trying to understand the single, dual, tri-band. Okay. So then came the 802.11ac. Okay. So as we saw, they also started giving out the numbers for it instead of having people remember these 802.11 and such. It's called Wi-Fi 5. Okay. They introduced some new concepts in there, and just to increase the throughput. And one of the most important thing was this concept of MU-MIMO. Okay. So before we understand MU-MIMO, MIMO basically is multiple input, multiple output, and it's actually a radio technology, antenna technology. Okay, that uses multiple antennas at the transmitter and the receiver to enable a variety of signal paths. Okay, for example, I'm sure you would have seen if you want to go and buy a Wi-Fi router these days, it comes with 6 antennas, even 8 antennas. So basically they use these antennas to provide the multiple paths to carry the same data through multiple paths. Because for example, if there is a transmitter and a receiver in a space, when you transmit something, it doesn't take the same path all the time. It's not like a wired communication, right? Wireless behaves differently at different times. I mean, wireless, maybe it's the humidity. There are so many factors that affect wireless. So wireless, when it comes to wireless, there is no predetermined path. It may bounce off differently from the last time how you send. So by having these multiple antennas, they can actually achieve something called diversity. So even if it bounces and reaches on the other side, if you have multiple receivers with multiple antennas on the other side, it can actually receive all those signals, and it can pick the best, because in Wi-Fi it's always there's always a chance of fading based on the environmental conditions. So you would want the best signal, and what better way to achieve that by having multiple antennas to receive and then choose the best. And it actually paved way for MU MIMO. It became like multiple user MIMO. So they thought, okay, we are using these multiple antennas for transmit and basically multiple input, multiple output. And they thought, why can't we use for transmitting to multiple devices at the same time? So you have like 4 sets of devices trying to communicate with 4 set of devices at the same time by using this diversity mechanisms, um, and see whether it can improve the bandwidth. And they actually achieved by having smart electronics on the receiver side. So basically these things cannot be supported, or it won't work in regular devices. So you need to have the endpoints be capable of all these, right? They even have advantage of finding out, detecting where his receivers are, and they can even do something called beam forming, so that like for example, when antenna is transmitting something, it will be like donut shaped, or it won't be like perfect donut shape. It may try to go all across, right? But with these multiple antennas, they can actually do a beam forming, which can actually let you transmit most of your energy, or use most of your energy to transmit towards one direction where the router knows that most of its receivers or the clients are. So there are multiple options. So it's a very exciting thing. If you want to do detail the class for this, probably we can do it later. I think Dauda can do it down the road. But there are exciting things that happen in that field, and it's a very highly loaded topic. We can do that later. Okay. So again, multi-user, MIMO is multi-user. It's already in use in multiple modern routers these days. And also, like I said, it can talk to multiple devices at the same time. Okay. Wi-Fi 6, that was the next one. In Wi-Fi 6, what they did was they were still using MU MIMO. They actually were able to do it instead of 4 devices at a time. They were able to do 8 devices at a time. Okay. They also had one more concept called OFDMA, that transfer orthogonal frequency division multi-access. So how they did was, if you can think of even in MIMO, if you have a channel to communicate to a device, they broke that frequency into subcarrier frequencies, subcarrier channels, small carrier frequencies. Okay. So the reason they did was, assuming it's a 5 gigahertz device, iPhones are 5 gigahertz, or even laptop, or even there are IoT devices that are 5 gigahertz devices. And you would think that when a channel, like you remember when we said clear to send, request to send, that problem is still there. You can call that as like a half duplex. Basically, you can't talk while you're listening. So it's one at a time, you talk, and then you wait for the answer, right? So if you are using this channel, like one of these big channel, to talk to a laptop, that is different from using that channel unnecessarily to talk to not talk, basically allow communication from IoT, which may be so lightweight, transferring so minimal bytes. So you are unnecessarily bogging down the carrier channel for during that period of time that these tiny devices are talking, right? So what they did was they broke that into subcarrier channels that allowed multiple devices to be to be basically it can send transmit or send data to multiple devices in the same channel. It's a think of like a truck, right? There's a truck that's going point to point, and you have a capacity, for example, laptop. It's a high capacity, but there are tiny devices that just needs to send few bytes or few kilobytes or megabytes. So they just broke it into subcarriers so that says the same truck can deliver, because they know that it's going to be destined, right, to all those devices that are under that range, under that Wi-Fi SSID. So that's how they efficiently manage. Instead of dedicating a separate clear to send RTS, CTS for these tiny devices, they were able to do that. But again, these devices should be capable of Wi-Fi 6. All the all the newer devices recently are coming with Wi-Fi 6. I think Wi-Fi 6 was ratified and started using, I don't know the exact date, probably November of this year, like just few months, September or November, just recently. But I believe already you start seeing these product in Amazon on the other stores. They already started selling. So this is pretty exciting, that it's going to increase your capacity to 10 GB gigabytes per second. I'm sure they won't, that be the maximum capacity. You will never get anywhere close to that anyways, but it gives you an option that you're efficiently using these carrier channels to communicate, right? The other one very exciting thing that they started doing is something called target wake time. Okay, what it does is it allows devices to determine when and how or how frequently they have to wake up and send data. For example, this may be a fridge that constantly sends its temperature or any other humidity or any other statistics. So if it were always on the Wi-Fi, like if it's always doing on the Wi-Fi, it's going to compete and create contention with other communication, because every time there is a contention, all the other devices back off, right? So what this one does is that these devices and the Wi-Fi router, because they are using Wi-Fi 6 and they are capable of it, they actually negotiate, and the router knows what time this guy is going to talk, like a periodically. Is it every 15 minutes, every 10 minutes, things like that. And the routers would actually knows that they need to allocate and make sure it has some clear channel for it to immediately transfer those, even those small bytes, and then they go to sleep again. So by doing this, you are actually removing that contention, where this has to participate, wait for others to stop talking and to send that few bytes. It's unnecessary overhead. And when it comes to IoT or any devices, power is always an important factor. There are so many IoT devices that maybe a remote, I mean, in your home, maybe hanging off of the roof, or so many things operating off batteries. And power is very important thing, because most of the power will be consumed by the radio to transmit and receive, right? So if power is a premium, with target wake time, it's a win-win, and it's pretty exciting development there. And one more very neat thing that they came up with is called BSS coloring. Okay, so let's assume if there are two wireless access points. Okay, when I say access points, this name is wireless routers. We can also call it access points. Okay, in an office floor. Okay, even though they are, say, in the opposite directions, say maybe this is east and that this is east and that is west, there will be still some weak signal overlapping, right? From the the other routers. Okay, so the clients always checks before transmit, because remember it is always clear to send, right? So if they both are in the same channel of the frequency of the one that's been used, they always wait and then try again, right? So if there is a client which is in this side of the building, okay, and if it falls in that range where there is a overlap, it's going to be using that back off mechanism to constantly back off and then try to contact. Okay, so by assigning color coding based on the BSS is called base service set. That is actually an ID that assigned to a device, or every access point or every router has something called a BSS ID. So based on the BSS ID, you can group and assign colors to those to those routers. Okay, so you can say blue, green, or whatever color. Those details will be transmitted in the Wi-Fi signals. So the clients actually sees all these information in there. And if, for example, user 2, this client wants to transmit and it sees some other activity going on, it inspects and then finds out, okay, it's not in the same color. So even if I transmit, it's not going to be a collision, right? So it transmits. It doesn't care, even though it's in use, because it knows that it's on the other side. So that's pretty interesting that actually they're trying to do. So if you're a Mac, I don't know, maybe there are PC, Mac. Normally you want to see a BSS ID. If you're a Mac user, you can, if you click option key and then click on your Wi-Fi, you would see take all this information, BSS ID. The other things that you can note down is the received strength, RSSI, the noise. Okay, the received strength should be towards 0. Okay, but nobody would get 0 anyways. Anything below 50 is perfect. Okay, if it's over 90, that means it's unbearable. You won't be able to transmit anything. Okay, so if you have those kind of things, you can look here. You can even look at the you can do open diagnostics. Okay, and then you can do if you go to window and then scan, it'll actually scan and give you what and all radios around you, and what kind of RSSI values they have, and how many people are in your own band using your own frequency channel that you are using. So there are multiple options. There'll be a separate topic to actually, if you want to go through how to optimize this and all those. I'm not, we can have some other session later, okay? We're not going to spend time on that now. So that is about the RSSID, BSSID and the color coding, okay? Is there anything in the chat? I see something in the chat, if somebody can check. Or we can wait until the end to answer. Okay. So let's go to the, what is time? 5:40, 5:44, okay. So advantages of wireless communication. The whole world is probably moving towards wireless communication, because gone are those days when people used to run Ethernet cable to the table, out to the desk, under each desk in the office. Nowadays, it's all wireless. So if you are into wireless communication, or as one of your future or your job, it's there. It's not going anywhere. So, and there are exciting things happening at the 5G level, even at the 802.1x level. I forgot to mention, I also said there is 802.11 AXE. Recently, the government has, I think they decided to allow 6 gigahertz range also to be added to this unlicensed spectrum. So I think we are going to have pretty more robust options down the road, and we are going to have like I think wired communication probably will die very soon, unless it's in the data center or server communication, those kind of things. So flexibility again is one of them. The overall cost of ownership is going to be less because when you want to have a wireless network in your office or even for your home, it's not that easy unless if you want to do that when you're building the home, it's pretty painful to run cables all across, those kind of things. What are the disadvantages? Again, as we said, one of the things I would say is the half duplex, basically speak one at a time, right? But because those things happen at microseconds level, you normally don't see all these contentions and the things that are happening behind the scenes, right? But still it's there. And especially when you're on 2.4 gigahertz, it's going to it's going to travel slightly farther than 5 gigahertz, but it's still going to be affected by all these other free channel interfering devices like microwave and cordless phones and such. 5 gigahertz comes with a better performance, but again, it has its own problem of things that interfere and the barriers that it can't cross because of a higher frequency than the 2.4. It interacts more with the surroundings and it actually gets attenuated very fast, much faster than the 2.4 gigahertz. So there are this barrier that actually I forgot to put the present again. So so you can see there are certain things that it'll actually interfere more compared to some medium. Okay. Okay. One other thing, the disadvantages with wireless communication is it's all open air. It's open to snooping, right? So it's been a constant struggle, like a cat and mouse game where people try to break into your communication. If it's wired, if you want to tap a wired communication, people can either somehow get hold of the routers, the intermediate routers. We'll cover about routers shortly, but people can hop into a router or actually physically tap a connection. So there are multiple options, but it's not obvious. I mean, it's not that easy to do. Whereas in Wi-Fi, you can be sitting in a Starbucks or anywhere that provides free Wi-Fi. There can be a master hacker sitting in the same room, trying to snoop and break into the communication. Okay, so they introduced originally called WEP, wireless encryption protocol. It was based on a very weak cipher, so it didn't stick for a long time. I don't think you would see anything WEP these days in any of the routers. And then came the WPA. Okay, so WPA also was on RC4, but it actually has had a shared key where you have a password that you have to have before you can join. Okay, but that also was disbanded because it still did not have the better cipher suite. So then they went into WPA2. WPA2 is what you see in most of the current setup, and it actually uses advanced encryption. It's called AES. and it's actually pretty much used by US government and other classified networks and stuff. So pretty much um, higher level security than the previous two versions. So it's still sticking. There are few things in it, W2A, PSK, TKIP. There, that's a separate topic. If you want to cover that, just remember that WPA is it uses advanced encryption and it's better than the other two. And even W2A, WPA2 had been tried to be broken into recently, or even sometime in the past. So the latest thing that they are settling on is WPA3. WPA3 has something called additional features that it has compared to WPA2 is it uses something called forward secrecy. So for example, when somebody captures all your data, even though they could not decrypt, they somehow snoops and captures all your data, and then they try to somehow get hold of the key. They can try to replay what has happened. So to avoid that, they started using something called forward secrecy, which basically rotates the encryption, decryption, encryption keys. Basically, it keeps rotating. So it's not like a single key that is used for a single communication. Again, if you guys are interested in encryption, maybe down the road, we can actually talk about it, have a class for it. But it's a pretty heavy topic. Okay, and I think we have, okay, I think we are on time. Okay, types of WLAN. So we've been talking about Wi-Fi, right? Wi-Fi is just a communication standard that shows how you communicate. But when it comes to WLAN, this is the one that you see most often, wireless local area network. It's almost like if you have a wired communication in your house with all the devices connected to a central switch, and they can talk to each other. Similarly, Wi-Fi, when you call it wireless local area network. So people use WLAN, Wi-Fi, quite they mix match. Okay. So typically, infrastructure mode is the one that you see normally that we have in our homes and offices. So it's pretty straightforward. There'll be an access point or a network that is connected to Verizon or any provider which is connected to the internet, and all these devices, they talk to the access point. That is pretty common, right? That's how most of our homes, offices are connected. We also had something called the Wi-Fi Direct that it's still in use. Some of the communications, like your cameras that has smartness built into it, laptops, not laptops, printers, where you can directly talk to those devices from your laptop or your other devices without having to have a access point providing that thing. But it's not like a standard form of communication that you can always use because it's a pain. But it's used for this kind of direct peering devices. So the second method is called ad hoc WLAN. This is another popular one that you would normally see when you buy an extender, Wi-Fi extender. It's basically a bridge. It's a bridge for the original one. And basically you put a bridge in somewhere across your home to extend that signal to a device on the remote side of your home, right? So it's just an extender. It provides that bridging capabilities. But still, the RTS, CTSs, or the owner of all those would be the main guy. So even though you're extending, you're benefiting by extending the range, but you're not benefiting by having that second device to be the controller for the communication. Okay, So it's just like a bridge. Okay, it's not like on its own. So that's why nowadays, if you go anywhere, you would see a mesh. That's the word that's out there. It's a distributed system where they have like three devices or four devices. They form a mesh. Um, so in this, it's almost like an extender. If you think it's like an extender, but each one of them can actually simultaneously or form its own zone. It can actually facilitate communication for the clients. And then it uses the separate band for connecting to the main guy. So it's called the main or the hub. There'll be a main or the hub that you'll connect to your Wi-Fi provider, either Verizon or any Comcast. And then you'll have extenders or the mesh extenders anywhere in your home. You'll strategically place it in such a way that you get full coverage so that there is no black spot. The advantage is when you compare with just a regular extender or a bridge is that these things actually act like a Wi-Fi routers. It's not just a range extender for the main guy. Okay, so if you have 100% coverage in this area, and then say originally before you had the extender, if you had 50% coverage or signal strength, by having these, you would have 100% again here and again 100% here. Okay, but if you have an extender, like in the previous one, you may get maybe 75, 50. So you previously, if it was 0, you will be able to get 50% signal strength, but still again, it's just trying to amplify the original strength. And the method of communication is also different, where he's the central owner of all those clear to send and request to send process. Whereas here, the mesh extenders act on their own. They talk to each other over a dedicated channel, and they make the information flow seamless. Okay, so that's one nice thing that the modern routers have. I'll have a link maybe when I send the PDF. You can maybe click on those links. It'll have interesting information about what are the options. Again, this will be a separate, this class is not about actually how to make your home Wi-Fi better. That may be a separate class, but we are not going to talk about that specifics in this class. So, okay, now we came back to the original where we started, right? So the core focus of this class was supposed to be what is inside that router or that tiny device that makes it so special, okay? And what concepts you need to know that happens within those routers that make everything work so seamlessly, okay? So networking, of course, networking is one of them, right? If you have, it provides you communication to the internet, to the world, and the packets or the data that you send, the request, the response comes back from the internet, somehow finds you, and then comes back to your laptop. So how does this know that you are the one who asked that, right? So networking plays a part, and the routing also plays a part, where it knows that, okay, the device is in guest network, and there are devices in home network. How does it differentiate and keep those isolated? So that's there. It also has a web component. We are not going to talk about it. It runs a lightweight web component that lets you log in, configure users, all those setting passwords, multiple other things, right? So this tiny box also has that feature. We have to talk about what DNS is, what a DHCP is, and has firewall options to prevent people from outside to try to create a communication channel or try to reach a device from outside unauthorized access, how to prevent that, and also how to allow only certain destinations to be allowed to go out. So there are multiple options. There are some modern routers that has also cloud options where it can not only check based on IP address, they can even filter based on the applications that you're using, like social media and like kids gaming times. You have multiple options. You can filter based on where the kids are going, what site they are going, what type of application it is. So there are a lot of intelligence built into uh, the firewall within the box and how it actually coordinates with the cloud-based firewall solutions. So pretty exciting things going on there. And one of the most important thing I always love is the NAT. We'll see why NAT, network address translation, is important. Okay. So before we talk about networking and routing and stuff, I know maybe people are already aware how all these things works, but I just wanted to put an analogy where how things move around, right? Say, for example, somebody's in an office building, is user user Z. He's working on a human resource department in one of the companies. He or she sits in floor 1 in suite 3389, right? So if a package needs to be delivered from outside, um, imagine normally a package gets delivered, maybe goes through security needs to allow them, and maybe it goes to a receiving department, and then the receiving department knows who sits where. So the guy signs up, and then he handles those packages himself and then delivers them to the right person. So if based on the location and the address details that he knows. Okay. So similarly, in the actual real networking world, the packages are nothing but packets, data packets. If packets are they're arriving to your office through internet. So the delivery mechanism is the internet, like previously, all those trucks. The internet is the one that facilitates packet movements. Those packets reaches your company. Most of the places they have a firewall, like the security guard. Most of the companies have border firewalls, but some of them don't do. But just assume there is a security that checks who's allowed or who's not allowed. And the packet reaches a router, and the router is the one that decides where it needs to send that data or packets to. So it'll have a table that has information about what kind of um, how many networks it has, how many will cover this, how many subnets. So like buildings or the floors, or you have subnets that you can break it into multiple subnets, and then there may be servers that is sitting inside a subnet that is running multiple services. One can be like a database service, the other can be like a file service, right? And in the communication world, TCP world or UDP or any network protocol world, the services basically run on their own ports. So we'll cover that in a little bit. So basically, if you look at a server that is running both the database, in this case, database servers and file servers, you have, even though it's the same server with the same operating system, two applications may be running on its own port, okay? And they actually listen for communication from outside only on those ports. So this is similar to the person who's sitting in a separate suite. He's responsible only for staffing. The other person is in the same subnet, same network, but they're responsible for payroll. Similar to that, they have their own functions and they listen on their own ports, okay? So all these needs to happen. For all these things to happen, there are specific information that needs to be in that packet to reach the correct destination, like an address that you need to put on the envelope. to reach a specific destination, specific suite in a specific building. These header information that have to be added in the communication, data communication. It's one of the most important things is these called phi tuples, whatever they call it. So it needs the source IP address. We'll see what a IP address is shortly if people don't know. There's something called source port, destination address, destination IP address, destination port, and protocol. So these are basic 5 information that is needed to successfully deliver a packet from outside to inside or from inside to an outside service. Okay, so let's start with the important things, right? What is an IP address? I know you would have seen when you connect to the internet and I mean connect to your Wi-Fi, you get something in say 192.168 IP range. You can do IP config command on your Windows box if you're Windows, or if you're a Mac, you can do IF config. You would see some IP address there that is showing up in your under your network adapter. Okay, so this is like a human readable format. Basically, computers don't understand all these. Computers don't understand only ones and zeros, binaries, right? But these are human readable formats that people created to understand this. So for example, if your IP address is 192.168.1.1, from the computer's perspective, it's going to be numbers like these. So I know everybody here knows how to convert a decimal to binary. That's not a big deal. You can do it. But if you are in an exam, for example, if you're taking an AWS exam and you have a question about networking and IP addressing, subnetting, and all those, there's no calculator there. So you would still need to understand this, especially if you're taking AWS Associate or higher, or even CCNA, Cisco, any of those. You would definitely get multiple questions on IP addressing. And the way I normally do is I just write these numbers 1, 2, 4, 8. Basically, it's 2 power 0, 2 power 1, 2 power 2, like that, all the way up to 2 power 7. If you write down in this paper, and if you want to get say 192, you would just put one on under anything that you want to make 192, right? So if I want to create 192, I'll put a 1 here, and then put zeros everywhere. So that's how we quickly find out. Okay, so we don't have to spend too much time on that. That's just an example, right? So this one again, it's not a big deal to find out, but if you're in an exam, you still need to quickly find out. So writing those 1, 2, 4, 8, 16, 32, 64, 128 helps you. Okay. And also when I spoke about 2 different subnets in a network, we need to first understand what is a network. Like it's almost like when like-minded people, they create a group, they want to communicate with each other, right? So similarly, network is like a grouping of resources or devices that want to communicate and share resources. They're all interconnected. They so if you have a big network with thousands of devices, and within those 10,000 devices, thousands of devices, you want to form smaller groups, say based on their job function, like finance and security would be on their own subnets. So in their own group of devices, you can further divide into smaller pieces called subnetwork. In short, it's called subnet. Okay, and so when you break that big network into tiny pieces, there is 2 things that you need to understand. One is called the network ID and the subnet mask. That is the one that's going to differentiate between which to find out which network a specific device belongs to. if you have like a big chunk, you broke it into 10, and these two information is important to find out. Out of that 10 10 small chunks, a specific device, whether it's in chunk 1 or chunk 2. So you have to make sure you understand this concept. Okay, so subnet mask is something that is important to find out, to see whether a device that is trying to communicate with another device, to find out whether that destination device is on the same network or on a different network. Subnet mask is used. So basically, all the computers have, when you are setting up your, of course, if you're doing it manually, you would find out. But if you're doing dynamically getting IP address, you will not see all these things. But assuming you are a network engineer, or you're doing something manually, subnet mask is something that your computer will ask if you are manually assigning an IP address to that device. Okay, so subnet mask is nothing but, again, you write in the binary format. Okay, and if you know the network address, and then you have a subnet mask written, basically it's a logical AND operation, and then whatever comes out of the output is what is used. So for example, if you know logical AND, 0 and 0 always makes 0, only 1 and 1 gives out the output 1. So for now, just remember that logical operation. Subnet mask just does a logical operational AND. Okay, so let's see how this one translates here. When so assuming you have a IP address, so as I said, 8 bits of zeros separated by dot. That's how you denote, right? Say, for example, you have an IP address of your computer 192.168.1.1, and you know that the subnet mask is 255.255.255.0. This is a human readable format again. And sometimes subnet mask is also written in this format. Like when you're a network, when you go out there, people may say CIDR, okay? When they say /24, it basically means how many consecutive ones are in that address. For example, there are 8 bits here, right? 8 bits, 8 bits, 8 bits. So there are 24 consecutive ones to make this address. So that is the subnet mask. So when somebody says /24, what it means, this thing, 255.255.255.0, okay? If somebody says /26, what it means is it's going to be 255.255.255.192. That will be the subnet mask, okay? So let's see how you derive the network ID from this address, okay? So when I write 192.168.1.1 in this format, as I said, I always write 128.164, this thing, right? Just repeat it 4 times. There are multiple other ways. I'm not saying this is the way you find out, right? There are multiple techniques. If you Google for it, there are multiple ways to do it. Just imagine this technique if you're using. Just write 192.168.1.1, that is the IP address of your computer, and subnet mask is 255.255.255. You convert that into binary format based on that technique, and then you do the AND operation. You do the AND operation of your IP address with the subnet mask, okay? So 1 and 1 will give you 1. 1 and 1 again will give you 1, right? So everything else that is not 1 and 1 is going to give you 0, right? So if you keep going, here the subnet mask, here it's 0, 0, 0, 0, 0, right? So no matter what you have here, whether it's 1, 0, anything, it's always going to be 0. It's going to be ending up, the value is going to be 0, right? So when you do the AND operation and find out the second computer in that network, okay, say your 192.168.1.1 wants to talk to 192.168.1.5, for example, okay? So you want to find out whether both the devices are on the same subnet or same network. When you do the AND operation, you would see that this section of your subnet mask that you specified it does not change. Okay, so the only thing that changes is on the right side of your subnet mask where you have 0. Okay, so anything that's all ones, that means it should not change. If they are on the same network, it should not change. So if you look at through this 192.168.1.1 and 192.168.1.5, if you go through this and look at this, that section would not have changed. Okay, so subnet mask knows after, I mean, the computer knows after it applies that subnet mask, it knows, okay, based on the subnet mask, 1.1 and 1.5 are on the same subnet. Okay, because it knows that anything to the left side of that unchangeable mask bits, it did not change. If, for example, if 192.168.1.1 wants to talk to another device that is 192.168.2.5, so what's going to happen? So assuming you have 2.5, right? If you apply 2, this section is going to change, because remember, the AND operation is going to be 1, 0, because it's instead of 1, you had 2. So it's going to be 1 and 0. And if you have an AND operation, so this section wouldn't have changed because it's still 192. This section wouldn't have changed because it's still 168. This section, because you have 2 here, when you have the AND operation, it's going to change. And the computer is going to decide, okay, I think 192.168.2.5 is not on my same network. So the computers have something called default gateway that you normally specify. That's where they're supposed to send that packet to. So the computers knows that it automatically, that it has to send those packets to the upstream router so that the traffic can be sent to the right device. Okay, so this is a concept you have to understand if you want to get well versed in networking, right? Very important to understand. So there are some examples that you can follow through to identify. I'm going to skip that. Okay, so when IP addressing is something, as you know, that IP addressing was actually created. It's like a address of your home. I mean, how people can reach you by getting the mailing address, right? Similar to the mailing address for the computer world or the computers. To get that logical address of your computer or your device, IP addressing is the one that is used. I thought I forgot to mention that before I started talking about IP address, but just remember that IP addressing is like any other address, right? So the IP addressing basically is assigned by an organization called ICON, and under that ICON there is a IANA, there is a division of it, that they are the ones who specifically assign IP addresses to the organizations, groups, universities, and multiple other companies and organizations. So when they started out, they found out that they started out with a big chunk. They devised this IP addressing scheme, and they found out it's very high, huge range. It's like almost like 2 million IP addresses that you can have with this many combinations, I think. So so 8 bits, 32 with 32 bits, if you put a combination and convert, you have like huge number of IP addresses, right? So they wanted to divide that into small chunks, because there may be companies that are so small, you want to give them a big chunk of IP addresses, right? So they broke down that class A address into, I mean, they broke down the IP address class into multiple of these small ranges. Based on the size of your organization, you may get a class C address, which has only option for 254 or even less number of hosts that you can have, computers or IP addresses that you can have in your network. Whereas if you have a class B network, you can have like 65,000 devices on that network. So when they started out, they didn't have a problem of, they didn't know that these things will run out so fast. And nowadays it's a premium to actually have, to get even a single IP address. For example, if you go ask Verizon for a single IP address, it's a premium. So why is it a premium? The IP addresses are the ones, as I said, are the ones that's going to make you communicate from, say, from your home all the way to the internet, say CNN or ABC or any of those you're trying to reach, right? So those IP addresses, the ranges themselves are routed by multiple routers on the way, and they all do only if it falls in this range. It's called a public IP address range, okay? And that is the range. They broke it into multiple classes, okay? And even with that, they immediately found out that they're running out of ranges, and because there are, each company may have like thousands of devices within their company, like printers and multiple other devices that doesn't even need to go out talk to internet, right? So you are unnecessarily assigning IP addresses to those devices. So they came up with another range. They carved out a specific range of IP addresses from within these big ranges. Uh, they called it private IP addresses. Okay, so the only requirement is these addresses would be only used within your own company or within your own home. Like for example, when you see an IP address that you get from your wireless router, it will be a private IP address in this range. It may be 192.168.1.1, or some homes you see 10 dot addresses. So these are private ranges which cannot be used to reach CNN or any public endpoint. Okay, so only the public IP addresses can be routed and be uh, um, used to reach the other side of the internet or other side of the town or other public resource. Okay, so just remember this, just to identify whether an address is a class A, class B, or class C. All you can see is if the IP address starts, the first address starts, if it starts anywhere from 1 to 126, you can immediately know that it's a class A address. So it's not a big deal. Nobody's going to ask you whether a specific IP address is a class A, class B. Maybe in some Cisco exams they may ask, but just for you to understand that if you have anything in the green, it immediately can find out what type of class that the IP address belongs to. And from within these ranges, remember, this may be an important topic for you to understand about the private IP addressing and what chunk of addresses from within those, the public range that has been carved out to be used for private address. Okay, and remember that private IP addresses are not routable. Okay, so you cannot reach a device on the internet using that private IP address. You need a public IP address. Okay, so the other thing you have to understand is protocols. Okay, protocols is something normally what a protocol in general means set of rules, right? If there is a protocol, that means there are a set of rules and regulations that you have to follow. Similarly, the internet also has some protocols. They basically use for organizing the data in such a way to ensure proper communication between two devices. The devices can be a server that is manufactured by Dell and the client that is manufactured by HP. So it may differentiate. It may be a different device vendor, manufacturer, but all of them have to follow some standards for effective communication between devices. So it's like a set of rules and the sequence of things that have to happen for a successful communication. between two devices. Okay, and there are multiple protocols. The two things that you would want to know the most is, on the most of the communication is TCP and UDP. TCP is a transmission control protocol. It's actually um, it's called a connection oriented protocol. How it works is, if a client, if sender wants to send something to another receiver, they first start a handshake. The handshake starts with it's called a three-way handshake. It's called a SYN-ACK packets. It's called a part of the three-way handshake. During that time, they negotiate their capabilities, how much they can transmit at a time, what is their pipe. So all those are detected during that phase. And after that, when they start sending packets between each other, they also acknowledge that they received the packets. So for every send, there's an ACK. For every packet that is sent, there's always a acknowledgement packet. So it's like a fully connection-oriented protocol, meaning that it's a guaranteed delivery mechanism where the sequence of packets that has been sent would be rearranged such a way that it's presented to you on your side. Okay, so there are some applications that you need to have TCP communication. It can't afford to lose packets, a lot of packets, and also if it's coming out of sequence, there'll be a problem. For example, email, if somebody is sending email in chunks where it comes through all the slide, and then if it's presented in a jumble format, you may not even know what that email says. Similarly, web pages that you're browsing, if it's all jumbled up out of sequence, you may not even understand what's written there. So there are applications that are very specific on all these. So those kind of applications, it's better to use TCP as a form of as a means of communication. So it uses TCP protocol, but there may be some applications that don't care. Basically, it's they call it like a best effort delivery. It's not guaranteed. It's called user datagram protocol, UDP, and it's also called connectionless protocol. So in this, the good thing with the UDP is there is no overhead. In here, you saw that for every packet sent, there is an ACK, and there is also retransmission if that ACK is not sent or received, right? So there's so much overhead to make sure that it's a connection-oriented guaranteed delivery. There's like too much amount of processing time and network bandwidth is utilized for these acknowledgements and the things, retransmissions and stuff like that. So they thought of why can't we use some other things, at least for specific applications who don't care if you get out of sequence packets. Just use something that doesn't even care about acknowledgement. So they came up with this protocol, connectionless protocol. And if you see an application like a voice over IP address, they call it like nowadays everything is VoIP. You don't see any analog phones in your home, I'm assuming. Maybe some homes have, but so everything over internet. Okay, communication happens over internet. So if you're on a voice call and you're saying something, the other side is a receiver. It's going to be a human being who can interpret what you're trying to say, even if you say some words are dropped, right? So he can even ask you, hey, I dropped some packets, or I didn't hear what you just said. Can you repeat? So those kind of communications, you don't have to care about what is getting dropped, right? Similarly, music streaming, having one or two blips in your music, doesn't care. Whereas if those kind of things, if it's missing and jumbled, or it'll be a problem for some applications, but some applications we don't care. So for UDP is very efficient and very suited for applications like this. Okay, so that's how that protocol came through. Okay, so the other concept that we need to understand is routing table. Okay, so what happens inside the, as I said, inside the router, your Wi-Fi, you and your Wi-Fi router, it needs to know whether the packet is destined to the guest wireless or the home wireless, home clients, right? Similarly, in the office, there may be a user and a printer in one subnet. There may be a server in another subnetwork, and there may be another client on another subnet. Okay, so a router is the one that knows if a packet from user one wants to go to a web server, the router will refer to its table. It's called a route table. Okay, it knows about all the subnetworks that is under it, and will create a table called route table, and it will have information where to send. It's almost like a name board or the direction board that you see on the highways. The board says, if you want to go to this network, take this path. If you want to go to some other network, take that path. So it's just like a path. It just tells how to go, right? And where to go, where will be the next hop. So if you want to go to the internet, your next hop is going to be the firewall or the border. Okay, so we'll see how it happens. Just remember, route table is nothing but it's like a information that shows where to go next. Okay. Okay, I froze for a second. Yeah. So if you are in an office in a bigger setting, you would see something more complicated route tables. So you don't have to worry about it here. It'll have multiple destinations and also consolidated routing. For example, router 3, it knows that to reach these two networks, even the third network, which is behind another router, it has to go through only one guy. He's the next hop. So just remember, router, just coordinate that piece, how to send traffic to the next hop. That's all. That's the information it has. Network address translation, one of the most important things that you need to understand. Again, why would you need a NAT in your inside your Wi-Fi router or in your office? Like I said, private IP addresses cannot be used to reach any device on the internet because those addresses are not routed by any public routers. Okay, those are primarily used. Private addresses were used primarily to within your organization, if you want to communicate devices within your organization or a printer that is within your organization, you can do whatever you want. But the moment you want to go out, you need to have a public IP address. So the NAT you can think of like an analogy. If you have C-suite corporate bosses who wants to publish something to say investors or media, they may go through a spokesperson who's like the middleman who translates or who's the public facing side, and he takes the data from them and publishes them. If you look at the content itself, content doesn't change, right? What they have wanted him to say is the same thing that he said, but they go through him because he is a public facing side for the organization. Nobody directly talks to those bosses. Okay. Similarly, in the NAT world, because you need a public IP to talk to any public device, public endpoints, you need to have a device that translates your private IP address into public IP address. Why would you even do that? Because public IP addresses are hard to get. Actually, they're running out of it unless you're a big corporation. You can't even get a big chunk of public IP addresses. So for example, in this company, it's a medium-sized company. Okay, somehow they're lucky. They got a class C public IP address, which is a /24, okay, which gives out around say 252 devices, because there are some reserved IP addresses that you may use for routers and also some other broadcasts that you don't have to worry about it now. So they somehow got lucky and they got that classy address, but inside their office there are like 3,000 computers or servers, right? So they can't have all those devices have their own public IP address, right? So that's the concept of having a private address inside your home, inside your office or your home. So the so they use the 192.168 address. So they break it into multiple pieces, subnetworks, right? And they assign they from this IP address they choose, you can choose one IP address. Oops. One IP address to be used as a IP address, the public facing IP address. Okay, so how it works, say a user one, he wants to say go to cnn.com. We'll cover what DNS is very shortly, but just say first thing happens always is a DNS resolution, because normally when you're typing cnn.com, but computers understand only IP address, right? So this is like a telephone directory that converts name to IP address. So for example, that happened. So user one sends traffic to a specific IP address that is assigned to cnn.com, say in this case, 151.101 address. As I said, how does the computer know that it needs to send to the router? Subnet mask, remember? It's going to apply the subnet mask on that, the 151 address, and it immediately know, okay, so this guy is not on my same network, so I have to send it to the router. Basically, the default gateway that you specify on your laptop or your desktop is the one that tells you what's your router's IP address is, okay? So that address, that packet reaches the router, and the router, as I said, has all the information about where the destination is. If it's anything that is not, that doesn't belong to its own network, it's going to send it to the default gateway or the default route, whichever is the next hop towards the outside, okay? So in this case, if it happens to be a firewall, it doesn't have to be firewall, it can be another router. You can do something called network address translation in those devices, on those devices, okay? So all it does is it looks at the packet source from 192.168.1.1, destined towards that 151.101.201.67. And what it does is it replaces the source address, okay, with this IP address, the NATed IP address that it should use. And then it uses that IP address, constructs the packet, and then sends that packet on behalf of the client towards CNN. Okay, and when CNN responds, CNN thinks it's talking back to the client on this IP address, because again, it's a public IP address. So that packet reaches the firewall, and then the firewall or any device, even a router, which is doing NAT, it has a table in it. It's called a NAT table that knows that is the table, for example, is just a representation. It may not be like this, but it has a table of all the information that it transferred and from who it came from, and how, when the response comes back, who to send it back to. So all those, it will be in the NAT address translation table. Yeah, it's called a NAT table, okay? So again, I said, remember, anything communication, you need a five tuples, whatever we call it. Source IP address, I'll say what source port is. You need destination IP address, destination port, and protocol. Protocol in this case is TCP, because you're trying to use a web application. Remember, web, I said you normally use a TCP protocol instead of UDP. So the destination port is something that you would have noticed when you're trying to go to a website. You type HTTPS, right? HTTP is a secure port, secure communication to your web server, and a web server like I said, web servers may have separate applications listening on separate ports. Those ports are the ones that identifies what the protocol needs to do, right? So in this case, HTTPS normally by default is port number 443. It may vary, but it's not static. By default, it's 443. So this is the one that we need to concentrate. There is something called source port, that is the port information of the when the client sends a packet. He includes the source port in that 5 tuples, so that that port information can be identified when the packet comes back. It refers to the guy who actually originally asked. For example, the second computer also went to cnn.com at the same second, same microsecond, same at the exactly same time when those two packets reach firewall. These source ports are the ones that's going to differentiate between those two packets when the response needs to go back. These source ports are actually randomly generated. Okay, they are called ephemeral ports. That they fall within the range of 1024 to 65,535, whatever the number is. Yeah. So the idea behind this is when two computers generate a random number with this big range, there's going to be very less chance for them to pick the same number, right? So that's why it's a random port. It's called ephemeral port. That the reason they call it ephemeral is that port information is used only for that communication. When that is done, when they want to talk to abc.com, if they generate another TCP session, that port may be different. Okay, so it's called ephemeral port. Ephemeral means temporary. Okay, and it is random. So you need to understand this concept very well if you want to become a good network engineer. Okay. So that's one thing. Again, here, if the user one wants to go to the web server of its own company, the router knows that it's here. It won't send it here. And if a user one wants to talk to user two, remember, the only time it will send the traffic to the router is if the computer finds out that the other device is not on its own network, right? The way it finds out, again, is using the subnet mask. Remember that very carefully. And I mean, register that. That's very important. Okay. So 1.1 wants to talk to 1.2. It's going to apply the subnet mask and then do an AND operation for those 24 bits from left to right, right? And then it knows that these three things are not changing, and only the last one thing changes. And then it knows that here also the destination is also the first three ones octets don't change, only the last one changed, and it knows, okay, so it's on the same network. That's the way it identifies. Okay. Okay, I don't know why my next doesn't work. Okay. DNS. Okay, DNS, like I said, it's like a phone book. Okay, it's like a contact list. In the olden days when they actually initially did IP addressing and stuff, people used to communicate in the very olden days, meaning like computer timings, right? The IT timings. That's not too old, but it's in the olden days. People used to even send traffic. They used to know their IP address of their device or the colleague that they're trying to communicate. So they were actually using IP addresses when they're communicating. And then when they started using or adding more and more devices, it was virtually impossible to remember those IP addresses. So like our phone book or a contact list where we have a name with a number that we don't have to remember. Similarly, DNS is like a phone book or a contact list with a name to IP address mappings. Okay. There are different types of DNS records, at least the two things that you have to remember, or I mean, at least understand, is A records and CNAME or alias record. How they differ is A record is like, if you look at the dictionary, if you look at the DNS database of a server, of a DNS server, A record would be have, like, if you have a name that you want to try to reach, right? If you want the name that you want to resolve, if the directory or the entry in it has an IP address, it's called an A record. Okay. And if you want to have a friendly name, for example, server1.abcxyz.com is a web server, and you are having you want to publish that name so people can easily remember to reach that web server. You can tell them to use server1abcxyz.com. It may be even a longer name, for example, right? But it'll be painful. But if you want to have a friendly alias name, like say www.abcxyz.com, or even abcxyz.com, it's easier to remember for people. You can instead have an alias record, create an alias record, or called a CNAME record for that original record, right? And then you create that record. So when a DNS resolution happens, it's going to resolve this CNAME, and then CNAME again. At the end of the DNS resolution, the IP address is going to be derived. But originally when they ask, they're going to ask that friendly name and the lookups done by your DNS server that's acting on your behalf. It's going to finally get you the IP address, but you have to remember only those friendly names instead of the actual server names. Okay, so remember those two concepts. And also there's one more thing to understand is when you are actually doing a DNS query, for example, www.cnn.com, you are actually sending that request to your wireless router. Similarly, in your office, you may have your own DNS servers that you are configured to. So when that request reaches those DNS servers, they are going to look up. So the lookup process goes through an interesting chain of events before your final answer is retrieved. Okay, so I have a link here. You can check. Okay, so there's something called root DNS servers. Okay, and then there's something called the top level domain it's called GTLD domain servers, which are basically responsible for those group of domain names that you have. You have multiple of those these days: .com, .info, .org, .edu. I think I repeated here, but so there are a group of DNS servers that are responsible for having the name of the DNS servers that are responsible for that for the domains. For example, in this case, abcxyz.com, you got a domain for yourself. You want people around the world to use your domain name and to reach, say, your www.abcxyz.com, right? So first you register your domain name, okay, and then your DNS servers that are responsible for abcxyz.com has to be known by these .com servers. So your name registrar, they call it registrar. What they do is they ask you to enter your name and then the name of the DNS servers that are responsible for that domain. Okay, so the registrar on your behalf does communicate with the icon. Again, the guys who are responsible for IP addressing, they're also responsible for DNS. So those DNS servers are updated with the updated with the address of the actual DNS servers where the actual record resides. Okay. Similarly, the icon also maintains the root DNS servers. That these DNS servers has the list of all the DNS servers that are responsible for .com, .org, edu, and multiple other. So when you are doing a DNS request, it goes through a chain of event. First, your DNS server or any other DNS server, first it's going to ask the DNS server, the root DNS server, hey, I'm trying to reach abcxyz.com. the root DNS server is going to say, I don't own that, but I know who is responsible for .com, okay? And it gives out the IP addresses, a bunch of IP addresses for the DNS servers that are responsible for .com. So then your DNS server asks this guy, hey, I'm trying to reach abcxyz.com. And these group of DNS servers, they say, I don't know, we don't own them, but we know who's responsible for that domain name. And they give out the IP address of this DNS servers that are responsible for your domain, okay? And then again, your DNS server asks directly this guy, hey, I'm trying to reach www.abcxyz.com. So the function of this DNS server is to look through its database. It's going to find out the name, corresponding IP address. It does the final job of getting the address. If it's a CNAME, again, one more query will come through, okay? But just remember that the DNS resolution happens and the answer is given to the original DNS server. So this is an interesting chain of events that happens before your name, for example, www.cnn.com is done. So, I mean, I've given like, if you want, you can have something like, there are multiple sites like this that you can do a dig that shows, for example, if I want to do www.cnn.com, okay, I can do a trace, okay, and then if I do lookup, it'll tell you, you see that it went through the root servers, okay, and then it went through the com servers, and then the cnn.com servers, and then the cnn.com said, okay, I own, it's actually CNAME record pointing to this server. Okay, so it's a concept that you need to understand if you are a good networking engineer and a DNS engineer. Okay, so that's one. It's a very important thing to understand. Okay, DHCP. We have time. Okay, we have 10 more minutes. Good. Dynamic host configuration protocol. The router does that too. Okay, so when you are joining, your computers are getting automatically an IP address. Okay, so normally when you open your Windows laptop or Mac laptop, you have a configuration that you can do to manually assign an IP address to your device, which will be painful because you need to add the information about the subnet mask, the default gateway. You also need to add the IP address of the DNS server, all those. It will become like unmanageable, right? So DHCP is specifically used for that and a few other things that it can help you with. Primary advantage is assigning dynamically an IP address to the clients. And along with that, you can also specify your subnet mask, default gateway, DNS servers, and other configurations that part of it. So it's a simple thing. It's not a big thing. DNS is more important, right? DHCP, it's okay to quickly browse through and find out what it actually does. Okay, and the other thing the router also does is keeps you, has a built-in firewall. Firewall, as you know, it's something that you write policies and rules to allow a traffic to either come in or go out or both the ways. There are multiple options to do that. It's basically, it's going to look at the packet. It's going to look at the source IP address, destination IP address, source port. I mean, not the source port, mostly it's the destination port that it matters. So it's going to look at that 5 tuples or 5 tuples to determine whether the traffic needs to be, or the data needs to be allowed to pass through or not, right? And there are 2 concepts that you need to remember within that firewalling. One of them is called a stateless firewall and a stateful firewall, okay? The difference is in stateful firewall is, if you have an analogy, if you take the concert hall, when somebody goes into a concert, for example, you may encounter a security person who checks you first, right? And then they give you a tag. Sometimes you can use the same tag on the way back because you already have a tag. You can go back and forth. You're through. You don't have You don't have to be checked again and again, right? Whereas in a stateless firewall, think of this as an airport immigration, specifically international travel, right? If you are going out in this case, out of the country, there's an immigration counter, they check you. And then when you're coming back, again, they check you, right? So similar to that, in stateless firewall, you are inspected for whether you're allowed or not every time you go out and come back in. Whereas in stateful firewall, when the first time you are allowed, you are given a token, and then as long as you have the same session token, they call it a session token. If you are on the same session token, you have your token is in the session table. It's not evaluated. The rules are not evaluated every time. Okay, so that's the difference between stateful and stateless firewalling. Okay, so a wireless router again does all these things in that small tiny box, and it's interesting that they could pack this much information, this much technology, apart from the antenna and the other all the other information, all other cool things that it does. It does so many things as well, right? So that's the objective of this class, just to show you what and all is inside there and what are the cool things it does. And also we slightly moved away and just went over the networking and other concepts that you may need to understand if you want to be a networking guy or a girl. Okay, that's all the slides I have for today. I didn't want to cover this packet tracer. Like if you are interested in core networking, there is a free tool from Cisco that we can explore later. But for this class, I think it's too much. Any question, guys?
I think everyone is sleeping, I guess. I don't know.
This is too much.
Yeah. Okay, then. Yep. Thank you, Saravanan. It was a really good concept here.
Okay, so maybe you can stop the recording.